Every digital interaction you take, streaming a video, sending an email, or trading stocks, is ultimately translated into a rigid binary language. At the foundation of all modern computing, tiny physical switches are either flipped off to represent a 0 or flipped on to represent a 1. Quantum computing bypasses that binary constraint. Instead of standard bits, it uses quantum bits, or qubits, which speak an entirely different computational language. To understand why this matters, look at how classical machines process information. Whether it is a smartphone or a vintage mainframe, classical logic demands that a computer solve problems sequentially, calculating one step at a time. A qubit doesn't wait in line. Because of superposition, it can exist as a 0, 1, or both simultaneously. Linked together, they exhibit entanglement. Instead of adding power linearly, each new entangled qubit doubles the system's combinations, growing power exponentially. This exponential growth is necessary because we're hitting a physical wall. Modeling a complex molecule for drugs or optimizing a global shipping network involves so many interacting variables that a classical computer would need millions of years of sequential steps to find the answer. The physical universe does not operate on a binary code. To accurately simulate reality's most complex problems, we have to build tools that actually apply the multidimensional rules of quantum mechanics. A classical computer navigates a massive maze using brute force, tracing every path and backing up from dead ends. A quantum computer leverages superposition to explore all routes simultaneously. Using interference, it acts like overlapping waves, canceling incorrect paths and amplifying the correct solution. Physicist Richard Feynman proposed this in 1981, suggesting the only way to accurately simulate physics was to build a computer natively utilizing quantum mechanics. Quantum advantage marks a crossover point, a moment a quantum processor completes a task in minutes that would have taken millennia on a classical machine. It represents a shift from computational guesswork to direct simulation. Harnessing this power requires extreme engineering. To keep the delicate qubits stable and prevent them from losing their state, quantum processors are housed in cryogenic systems, chilled to a fraction of a degree above absolute zero. At these freezing temperatures, the materials in the processor become superconductors. Electrons move through them without resistance, allowing scientists to manipulate the qubits with microwave pulses while shielding them from outside heat or magnetic noise. You don't need a multi-million-dollar dilution refrigerator to run these algorithms. The delicate hardware is maintained in specialized labs, and users access the processing power entirely through the cloud. Open-source software development kits, like Qiskit, allow developers to use standard Python code to send instructions directly to quantum processors. This shift hasn't erased the physical challenges of scaling these machines, but it has removed the requirement for researchers to maintain their own labs. The ability to test quantum logic is now available to anyone with a browser. But a machine designed to quickly untangle highly complex mathematics can also be used to intentionally dismantle it. In 1994, a mathematician named Peter Shor published an algorithm proving that a sufficiently powerful quantum computer could quickly factor immense prime numbers. That process targets the mathematical bedrock of current encryption standards, like RSA and ECC. The security protecting private bank records, encrypted messages, and national security networks relies on factorization that a quantum machine can bypass. The exact same superposition and interference mechanisms that allow developers to simulate life-saving drugs also create a systemic vulnerability for global digital infrastructure. To defend against this, cybersecurity experts are transitioning to post-quantum cryptography. These are new encryption algorithms built on math problems that are too complex for even quantum computers to easily solve. Companies cannot afford to wait for quantum hardware to mature. Securing data now requires a hybrid approach, layering these new quantum-safe algorithms directly on top of existing classical security systems. Major research institutions and government standardizing bodies have already finalized these new protocols, pushing the tech industry to migrate its infrastructure immediately. We are entering a period where the software we write to discover new materials is the same software that requires us to overhaul our digital defenses. Navigating this means learning to code for a world where complexity is no longer a safety net.